Hi, my name is Vahan Davudyan. I'm a physics experimentalist for 34 years, and today our topic is kinetic energy, which is extremely important concept. And this is the logo I created. If you click on this logo, you can see all my 78 theories. So it's called Unique Physics Concept by Vahan Davudyan, How to Promote the Science. And this is my email, vahandavudyan1948@gmail.com. I have simplified the kinetic energy. It's going to be so comprehensive, you're going to love it, because I have done some experiment I haven't seen in any physics books, and this is going to be so important, and I'm hoping that you guys will love it. And anything in motion, from the molecules all the way to the planets, even this is small rolling balls, whatever moves, they have a kinetic energy. But I show you the formula and everything else, and these are the ramps by Galileo, which was like 400 years ago, and this is like a low incline and the high incline, and anything in motion like an asteroid or meteors, or when you walk, when you fall, airplane or baseball player or anything in motion has a kinetic energy. And in fact, this was developed by Daniel Bernoulli, great scientist, Swiss mathematician and physicist, in 1738, and later it was developed and formulated. And the most important people who worked on this was Sir Isaac Newton, and on top of that was the, Miss Amélie de Châtelet, the French scientist. She formulated, and this was amazing. And kinetic energy is used everywhere. I mean, whatever has a motion, even the planets, I will explain later. But I have to explain a little bit about Sir Isaac Newton and Amélie de Châtelet, the French scientist. And this was amazing. This was formulated later, not with Daniel Bernoulli. But the most important person in this formula was Amélie de Châtelet, and then I will give you the formula. And she was so amazing. She didn't have college education. She was, educated, and she was one of the brightest minds in the history of physics. So in fact, her husband, the first husband was, in army and then was always traveling. But the second husband was Voltaire, which was a scientist. And unfortunately, he had a problem with French government, and he was always in the run. And then I remember one day he went to Holland in Netherlands. Then he saw an experiment. It was done with, William Gravitational, the physicist. And then before that, people were thinking if you drop a ball like this, steel balls or brass ball in a clay, if you have like a velocities 1, and then if you increase it to 2, it's going to be penetrated 2 times. And then Mr. Gravitational showed that no, it's squared. So when the velocity is doubled, the penetration in the clay is going to be 4 times. So immediately Mr. Voltaire, wrote a letter to his wife Amélie, and then she was great scientist. She had so many pendulums, and then she checked with pendulum, she checked with the clay, and then she dropped the ball, and then she realized that's absolutely true. When you increase the velocity by 2 times, the penetration or the kinetic energy is, squared. And that was amazing. After that, this has been almost like more than 200 years. And then she formulated this. And in fact, these are the, incline, they call it, or, ramps for Galileo's, and then we have a low incline, and then we have a, like a high incline, and it doesn't matter how you do it. And then whenever you have like a rolling by like this, always they increase the velocity. And in fact, this is the one I have never seen in any books or anywhere. We have like and Kepler was one of the greatest scientists in history. So this is the Mars in an orbit of Sun, and you can see this is a small, this is narrow, and this is wide, and this is called apogee, and this is called perigee. And then Kepler was amazing, scientist. He realized that, orbits around the sun is not round, it's elliptical. See, this is like an ellipse. See, he called it elliptical, and that was his first motion. And the second law for the planetary motion is that if they come closer to the sun, they travel much faster. When they're farther from the sun, they travel much slower. But you can see this triangle is smaller and this triangle is much bigger. But they are exactly travel in the same interval of time, and then it's equal time, equal, So this is the Kepler's second law, but I had to analyze and reanalyze so many years, and finally I came to this conclusion that, nobody explained why when the planets, it doesn't matter, Mars, or, anything, Jupiter or, any planet comes closer to the sun, they travel much faster. When they're farther from the sun, they go slower. And like I said, this is called apogee or apogee, and then perigee. And my logical explanation is this, that, that's because of gaining kinetic energy. But I will explain why. When the Mars is going around the sun, and imagine here is much closer, and here is so farther from the sun. But the way it is here, it has gained some gravitational potential energy, but right here is almost half and half. But right there is getting closer to the sun, and this has more kinetic energy and goes much faster. And here is the same thing. So comes here, more gravitational potential energy, and here goes much faster. And in fact, I have seen this because I had pendulum, which was great success. I published this like 2 years ago. Pendulum is the same way, even though it's not like 360 degrees like planets, but it's the same thing because it's going back and forth. So gravitational potential energy is converted to kinetic energy, and kinetic energy is converted to gravitational potential energy. And of course, later I will explain. I made my own ramp, and then I will explain how this works. But before I do this, I have to explain the Galileo's contribution, he was great scientist. We put this up. Galileo was an amazing scientist, and then at that time there was no clock invented. It hadn't been even invented. Then he was in a church, and then he realized that the chandelier was going back and forth, and then he was genius. He got his pulse, and then he realized all those swings, small swings or the big swings, are exactly the same. Well, of course, it's a long story. Then he rushed home, and then he tried it with his pendulum, and then he made his own ramp like this, and then he was genius. He realized that if you roll this, I think it was brass balls, he rolled this on the ramp, it accelerates. So the acceleration is so important. And then he came up with this formula. Well, of course, at that time when the Galileo did this, there was not anything, no one had any idea about the kinetic energy. And he came up with this idea that the velocity is equal to acceleration multiplied by time. So when he rolled the balls, then he realized that the intervals are getting larger and larger and larger. Because at that time there was no clock. He was so genius. So he just invented these things, He just run some, from the faucet, and then he realized that one notch is going less. 2 notches is going 4 times as much. And he realized that, whatever, is in motion always gets the kinetic energy. Well, of course, like I said at that time, he didn't know about the kinetic energy, but he formulated this. So that was his idea, that the distance the ball travels is half of the acceleration multiplied by times the square. So nowadays we know that if you drop a ball, so of course this formula for the Hallelujah, it works for the falling ball. It doesn't matter, like a falling ball or rolling balls is exactly the same. In 1 second, the ball falls minus 4.9 meters. And then in 2 seconds, it's 19.6. Why? Well, of course, at that time, like I said, there was no 2 seconds. He was going with the notches. And imagine, so it's 2 times 2 is 4, 4 times 4, so that's going to be 19.6. And then 3, so it's 3 times 3, which is squared. And then it's going to be, see, it's going to be, velocity is going to be 24.9. And imagine, 4.9 meter, and then it travels 19.6 meter. And then in 3 seconds, it travels to 44.1 meter, and all the way to 10 seconds. So this is the kinetic energy, formula. Like I said, it was with Amélie de Châtelet. It's the kinetic energy is half of the mass multiplied by velocity squared. And this is so important that, if you have like 10 seconds because I, calculated with 100 grams of steel ball like this, and then I came up with this, figures that, it exactly takes 98, see the velocity is 98 meter per second. So if you multiply 98 by 98 and then multiplied by 50 grams, which is half of this 100 grams, you come up exactly with, 4,802 joules. This is only for 1 second. For 10 seconds, you come up with 480,200. So this holds true for anything, if you drop a ball or if you drop anything, as long as there's no friction, so that goes for the formula. And in fact, I had to compare that, when the asteroid 65 million years ago hit the Yucatan Peninsula in, Mexico, that was equal to 10 billion atomic bomb. Can you believe when, it's creating a lot of heat, it's creating a lot of energy and the shock waves. So in other words, all the dinosaurs died because of the asteroid. And then imagine if the 2 tons asteroid come, that is going to be 9 billion, 6,004,000 joules. And imagine that is so bad. So the most important factor for the kinetic energy is the velocity and mass. Because according to this formula, if the mass is doubled, so the kinetic energy will double. If the velocity is doubled, the kinetic energy will be quadrupled. So in other words, it's multiplied by itself. I have another one. Let me post this up for you guys. You can see. Of course, you have seen this in parks, always, that people do like a Magic Mountain in California and places like that. When they go up, they are, having potential energy. When they come down, they have the kinetic energy. And in fact, this is a simple one showing potential energy. But the important fact is, she invested energy. So she dropped, she got the ball all the way to this top. So probably this is 10 meters or what, I don't know. But she invested energy. When you drop that, it has potential energy. When it comes down, hit the ground, so the kinetic energy converted to heat, because it depends on the impact, how big that ball is, and then it creates a little bit heat. And like I said, like asteroid is going to create a lot of heats. And then this is the one showing potential energy transforming into kinetic energy. And if you come exactly in the center, exactly in the center, so potential energy is half and exactly the kinetic energy is half. But here is the maximum kinetic energy and the potential energy is zero. This is used in, like a creating electricity and so many other things. This one is showing the asteroid or meteors are coming down, and imagine most of them, the small ones, they vaporized in atmosphere, but the big ones, God forbid, if they hit the our planet, that is going to be so devastating. Even the city will demolish everything because of gained kinetic energy. And I have another poster. This was amazing scientist, French mathematician and scientist. His name was Louis Lagrange, and that was amazing. That was breakthrough in science. That's why we had to do the James Webb telescope, because we had no idea this was going to work, but it worked. But this Lagrange was an amazing person. In 1772, he came up with the idea, if you have two masses, he was talking about like Sun and the Jupiter, Sun and the Saturn and things like that. And the third one will balance itself, so you need a little bit energy to go around. So, and he called them Lagrange point, and then you can see here L2, L1, and then L4, and then L3. So it was in 1772. And in fact, this was substantiated in 20th century. This was called, this was called Trojan asteroid, and which was, trapped between here on L4. And imagine, you don't need any energy. You don't need any kinetic energy. As smallest, thing, it will go forever. So it was trapped here. It was going forever. So as long as there is nothing acted on it, so it's going to be okay. And amazing, when this, mathematician formulated these things, Lagrange point, now we know that, Galileo, Sir Isaac Newton, they were right about the first law of motion. If there's nothing acted on anything, they can go in a straight line forever. But now, this is going in a, circle. This is going in a, like a loop forever, because I have no idea how big that asteroid was, that, Trojan, but it goes forever. Because, over there, 1.5 million kilometers above the Earth, you don't need anything. But the bad thing about the James Webb telescope is it cost us like $25 billion. But unfortunately, if something goes wrong, we won't be able to get there and fix it. And I remember in 1990 when they launched the Hubble telescope, it changed our understanding about the universe, about the Big Bang and everything else. But unfortunately, there was something wrong with the lenses. They were getting out of focus, and then the pictures were blurred. And then imagine, like 400 miles above the Earth, it's not a big deal. We can travel in, easy. Few minutes. So they went there, and then it was so difficult, but they fixed it. And then when Hubble sent so many things for us, and then we realized that, it changed our understanding about the universe and everything else. And I'm hoping that, they still use it, but unfortunately, it looks like the Hubble telescope is going out of commission soon, but I'm not sure how good. But that is the main advantage of the Hubble telescope versus the James Webb. But James Webb is so good. And imagine the old days Galileo was doing, from the Earth, and then always, the atmosphere is in between, and it's exactly, we are not seeing exactly everything. In other words, when you watch the sun, that's not the exact location because light is refracted. But, above the atmosphere, the way the Hubble did, that's exactly right, and that's the way it does. I have to show you something. Galileo, when they did this, so this is like a cue ball. You know what this is. It's like a hilliard, you're playing with this. This has 176 grams. And it doesn't matter if you drop this, and then what happened, that the impact point is going to be a little bit hot. But if you drop this one, this is a bowling ball. This is 5,470 grams or 12 pounds. This is going to damage your house. If you drop this like 10 seconds, that's going to damage everything because of gained kinetic energy and more mass. Of course, I had to invent my own ramp, and I came up with this genius idea that, you know what, ramp is not supposed to be half like this. Ramp is supposed to be like V-shape. And then why did I do this when I displayed this in year 2000 in Regis University? There were so many professors, they loved this idea. The reason why if ramp is like this, the way Galileo did, so you can see 1 second, 2 seconds, 3 seconds, 4 seconds, and then you can calculate everything. But the way I did this, that is unique. And then I don't remember having seen this anywhere. So what it does, it travels all the way to this 0 point here, or the center, and then the gained kinetic energy will propel this to the other side. And they love this idea, so I'm going to show you. So when I have like 72 grams and 36 grams, I'm going to display, and then you can see how important it is. You know, this is the only way you can see, understand why the kinetic energy, anything in motion, has kinetic energy. And by the way, this is exactly 100 centimeter or 1 meter, and then I calculated with great precision, and this is only 1/10 of the gravity. So it takes exactly 1 second to get over here, and then 1 second to go to the opposite side. So I'm going to I'm going to roll this 36 grams and 72 grams simultaneously so you can see it. I forgot to mention something. According to Galileo, and then after that we proved that, you know, anything in free fall, it doesn't matter. Even though we have like friction, everything falls at the same rate. Well, unless if there's no friction, but sometimes friction makes a big difference. And you can see here, see what happened. They go out of sync. The reason why, that 72 grams gaining more kinetic energy. But you know, 36 grams is getting less kinetic energy. But I don't want to waste your time. After a few minutes, what happened, this 36 grams stops. See, now you can see it's going almost. And this is graduated. These are each color is 5 centimeters. See, now you can see this 36 is going almost like 15, but the 72 is going almost like 20 centimeters, see? Finally, this 36 is going to stop. The reason why is gaining less kinetic energy, it has less mass. So this is the only way you can visualize why kinetic energy is so important. See, now stop, but this 36 is still going on. This is exactly what happened in the pendulum. And imagine when Foucault did this, and I was in Paris a few years ago. I was there all day long in Pentium, and he was one of the greatest minds in history. But imagine his pendulum was 28 kilograms. And then I calculated it was, you know, creating almost trillions of joules because of, you know, it was going 8 seconds. You know, 8 seconds in a science is a lot. So it was 8 seconds back and forth. It was going in that, Pentium. And then imagine it rotated 360 degrees, and people have no idea that the earth is rotating. They knew, but you know, this was the first proof. This is another thing I show you, and then you are going to love this, because see, I have like 36 grams, you know, just in a center. When I roll this, see what happened. have to try this again. Let me roll this. See, it traveled exactly 1, 2, 3, 4, 5, 6, 30 centimeters. If I replace this, see what happened. And that 72 is not going to travel that much. Did you see what happened? 72 only traveled 2 notches, or let me show you one more time. So 72 traveled only 10 centimeters because each color is 5 centimeters. But if I do the 72 versus 32, did you see what happened? 1, 2, 3, 4, 5, 6. It traveled 36. So what happened as this rolls is gaining kinetic energy. So thanks a lot for watching, and I'm hoping you guys love this. And then if you have any concern or anything, you can email me, and this is my email, bohandawudyan1948@gmail.com. And this is so important, so I hope you like it, and then if you like it, you can subscribe it. And thanks a lot for watching, and your ideas always I put it in work, and then I honor your ideas, and then always I try to make sure that whatever you ask me, I will do it. Thanks a lot. Bye bye.